Hello, my young chemists. Well, today, I'm sorry, it kind of took a little bit longer than I wanted to. Um, I want to go over lessons 77, 78, and 79. I'm going to do it pretty briefly, but hopefully hitting the key points that will get you through the book assignments that you're going to need to do to turn that in tomorrow before midnight. Along with your, what is it, 74, 75, and 76 assignments. Um, but anyway, first thing I want to do is just start with lesson 77, looking at the chem catalyst. It says you got 12 nickels, two aluminum cans, and a balloon of carbon dioxide. Then it asks, well, which one has the greatest mass? Well, this is a tough question because it doesn't tell us how big the balloon is. If we made the balloon, this big, it could have a very large mass. But my presumption was, you got this regular size balloon, maybe the size of about two heads. Um, then you got your 12 nickels and you got your two aluminum cans. So the one that has the greatest mass is going to be the nickels. The nickels end up being a little over 55 grams. The aluminum cans are roughly 27 grams. And then the uh, balloon would be about 44 grams. Well, the next question then is, well, which one would have the greatest number of atoms? Well, to answer this question, we got to think about, well, how many moles are there? Um, and as it turns out, each one ends up being about 1 mole, 55 grams of nickel, 27 grams of aluminum, and 44 grams of carbon dioxide are all about uh, um, 1 mole. So since 1 mole is one chunk that is 6.02 times 10 to the 23rd atoms, what we're going to see is that they all have about the same number of atoms inside of them. Now, one other thing that we'd want to look at there is, how is this worded? Is it worded as the number of atoms or number of molecules? You may need to take CO2, being that there's a C there, an O there. Can't get my fingers in there, and another O there. There's three atoms there. So you'd have to multiply the 6.02 times 10 to the 23rd, and you would end up with 1.8 ish times 10 to the 24th total atoms of carbon, oxygen all together. So, anyway, you just have to be careful how the question's worded. Um, what I then wanted to take a look at is, I left page 6 of the slides open because it was originally my intention that I was going to talk while we went through the slides and blah, 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 blah. It didn't work out. Okay. I tried and just, it wasn't working. So, what I want to do now is that slide on the board and just sort of walk you through the process of finding the molar mass of a particular substance. And we're going to look at aluminum chromate. And so aluminum chromate is Al2CrO43. Now, to find the molar mass of that, we need to take each one of these atoms, each one of these elements in the compound, and break it down to each of its parts. So if we look at aluminum here, there's two of them. Okay, and so two aluminums is going to be 2 times 27. Again, I'm looking at the periodic table here to come up with that 27. That would give us 54 grams. Okay. Then if I look at it, I've got chromium, but one mistake that people often make is they go, oh, okay, well, I've got one chromium. Well, you don't have one chromium here. You've actually got three. And so 3 chromiums, that's 3. And if we go to our periodic table, chromium is 52. And again, rounding to the nearest whole number can be very helpful. This is actually 26.98. You look at chromium, it's 51.996. Make it easy on yourself. Make the math easier. So 3 times 52 is 156 grams. And then I've got oxygen, but not 4 oxygen, but 4 times 3 oxygen, or 12 oxygen. So 12 oxygen is 12 times 16. I didn't know this off the top of my head. I calculated before I did it, is 192 grams. So if I go ahead and I add all of those up, 6, 2, and 4 is a 2. Carry the 1. 6 and 5 is 11. Plus 9 is 20. And then carry the 2 there. I end up with 402 grams per mole of aluminum chromate. And so that's kind of the process you're going to need to do on a couple of problems in the homework, a couple of the problems that are coming up on your quiz next Monday. But basically, make sure you understand how to do that. If this isn't making sense, again, email me, tyrick@auhsd.net. Your check-in for 77 was you have 1 mole of oxygen, which is O2, and 1 mole of carbon dioxide, which is CO2. Which one has the greatest mass? Well, oxygen is 2 times 16, or 32. Carbon dioxide is CO2, so it's 2 times the 16 for the oxygen, plus 12 for the carbon. So that's 44 grams. And so the carbon dioxide balloon is going to weigh more. And then the second question is, which has the larger volume? And to answer this question, we have to go back to, the gas laws. Avogadro's law says, hey, if I've got equal numbers of moles of a particular atom, if all the other conditions are the same, then we're going to end up with the same volume. So both of them should be the same size. All right. Now, to move on to lesson 78. Lesson 78, you had a question. It was, you've got 1 mole of arsenic and 1 mole of arsenic oxide. Which one is going to have the greatest toxicity? And so this boils down to, well, what's going on here is I've got AS compared to AS2O3. Well, if I have 1 mole of AS, I've just got 1 mole of AS. But if I've got 1 mole of AS2O3, there's 2 ASs in that 1 mole. So there's actually 2 moles of the arsenic in that AS2O3. And so by virtue of the more arsenic in AS2O3, it is going to be more toxic. All right. And then there was another question. If you compare 1 gram of arsenic oxide, AS2O3, versus arsenic sulfide, AS2S3, what it boils down to is which one of these is going to have the lowest molar mass. The one with the lowest molar mass, with the virtue of 2 ASs in both of them, more is going to be arsenic if it has a lower molar mass per gram of it. So the arsenic oxide is definitely going to be more toxic. Now, a little better question that I would have brought up if we were in class is, let's say I also threw in, 1 gram of arsenic. Well, if I threw in 1 gram of arsenic, the whole sample is now arsenic, and it would be the most toxic. So we don't even have to really worry about the fact that that 1 gram is, has some oxide or has some sulfide in it, it's all arsenic, so it's going to be the most toxic. So, what this boils down to then is we're trying to compare moles and mass. And when we compare moles and mass, what I've found through the years is that a little schematic always, sort of helps. And so I'm going to try and explain this to you, try and show it to you here in the most effective way possible. So when we're trying to go from, grams to moles to atoms or atoms to moles. Boy, it's hard to do this. It's a little bit backwards. The idea is that we're either going to multiply or divide by two simple numbers. And so to go from moles to grams, what I would want to do is take a look here at the arrow. It's multiply. What do I multiply by? I multiply by the molar mass. So if I had 2 moles of oxygen and I wanted to know how many grams that was, oxygen again is O2. So O2 is 2 times 16, that'd be 32. If I had 2 moles, 2 moles times 32, the molar mass, I would end up with 64 grams here. Now, what if I had the number of atoms, but I wanted to go to the number of moles? Well, this is a case where I've got, 6.02 times 10 to the 23rd. I'm going to go this way, so I'm going to divide. So let's say I had 1.8 times 10 to the 24 atoms. If I divide that by 6.02 times 10 to the 23rd, I'm going to end up with 3 moles of whatever I'm talking about. Now, one thing that people often get confused with is what sort of numbers should I end up with for grams, moles, and atoms? When I look at grams, generally we're going to be dealing in chemistry somewhere between 0.01 to roughly 1,000 grams. Okay. Moles is usually a little bit less than that, again, because we're dividing by the molar mass. Generally, moles, we're going to end up somewhere in the range between 0.001 moles and usually 10, but we might run into a problem, especially if we're dealing with something on an industrial scale where we've got 100 moles of the substance. Now, as far as atoms go, what you have to remember is that atoms are really, really big numbers. They're going to be, 6 times 10 to the 20th to, 7 times 10 to the 26th. They're going to be really, really large, large numbers, big, numbers that are going to have 20, 30 zeros on the end of them, that kind of thing. So they're really, really big numbers. All right. Next question that I wanted to talk about was the check-in on lesson 78 was 11 grams of chlorine gas. So if I have 11 grams of chlorine gas, what is the number of moles that I'm going to have there? So let me just sort of do a little squiggle there. But 11 grams of chlorine gas, first thing we got to do is figure out what is the molar mass for chlorine. And so, again, chlorine, I've got 2. And then chlorine, because it's not above 0.9 and it's not below 0.1, I always like to use those numbers that are between 0.1 and 0.9. Otherwise, just round them up or round them down. So if we look at chlorine, it's 35.45. And so if I take 2 times 35.45, I end up with 70.9 grams per mole. And from there, basically to go from the 11 grams to the number of moles, I go back to my little schematic and I'm looking at the number of grams, which is right here, 11. I'm going to divide by the molar mass, 70.9, and that's going to give me the moles. So if I go 11, divide by 70.9, punch that into your calculator, you get 1.55 moles. Now, how do I know it's moles? Well, this is grams per mole, and this is grams. So the grams are going to cancel out. You've got 1 divided by 1 over mole, which leaves you with moles. And so 0.155 moles would be your answer there. All right. And lesson 79. Lesson 79 to me in the past has always been kind of problematic, kind of confusing. So you just have to kind of take it slow. First thing you need to ask yourself is, what are they asking me in the question? Do they want to know moles per kilogram, or do they want to know grams per kilogram in order to figure out the toxicity? And so inevitably, because you're dividing by the molar mass, the mole per kilogram toxicity, LD50, is going to be less than the grams per kilogram or whatever we're talking about. So this one it sort of poses a dilemma that we ran into back in the 70s when we first started looking at these artificial sweeteners. Basically, why did we want to use these artificial sweeteners? One, it cut down a lot on calories. Two, is that you could chemically manufacture these sweeteners and they were cheap. They were very cheap. That was why they originally made them, is that they were trying to make the sodas cheaper by using less stuff to make them. And to me, diet soda tastes like garbage. I just don't like the way the sweetener tastes. So, not great, but if you want to not take in so many calories, definitely it's a way to go. It's also, although this is under debate now, maybe better for you if you've got diabetes or something like that. They're showing studies now where maybe even the artificial sweeteners are worse on your diabetes. So be careful if you've got diabetes or somebody who does. Look into it. But the idea here is, the question in the Chem Catalyst was, you got a regular soda, you got a diet soda. Which one of these is going to be more toxic? And there's many people who would debate this. Oh, well, sugar that goes into this is natural, so it's got to be better for you. The diet soda, it's chemically made, it's not natural, so maybe it is less toxic. But or maybe it's more toxic. But anyway, the diet soda ultimately is not using very much of the chemicals. So it's not you're not getting a whole lot of the stuff that could potentially be bad. And so there's this whole debate throughout the chapter or the lesson that I would really recommend that you read on how they determine which one of these would be more toxic. And as it turns out, the fructose in the case of aspartame is actually more toxic. Now, back in the 70s, they were looking at a substance. The first artificial sweetener was called saccharin. And saccharin was, I think it's in Equal. And, if you've ever watched the old TV shows, they were drinking Tabs and things like that. I don't think Tab exists anymore, but Tab, they were giving the saccharin to rats. And what they found out is that the rats were getting cancer. And so there, was this big debate. Should we warn people? Don't, drink these saccharin drinks because you're going to get cancer. Well, as it turns out, it wasn't even a realistic study because they were filling these, 2 or 3 ounce rats with, you know, half their weight in saccharin every day to give them cancer. So it wasn't a great study, but it was kind of scary. People went, don't drink that. So from there, I would go through the lesson again. If you have any questions, read it. If it's still not quite making sense, give me an email and we'll talk a little bit more about it. And then the check in was if you had equal LD50s on 2 substances, would you rather have 1 gram of the larger molar massed substance or 1 gram of the smaller molar massed substance? And the idea here is you would want the one with the larger molar mass because you are getting less of the substance at that point. So, in that 1 gram. But I hope this helps. Again, I can't stress enough. Go back through 74, 75, 76 before the quiz. And that's going to happen Monday. If anything comes up, again, I'm checking my email through the weekend. You can even email me before the quiz, before you're planning on taking the quiz, about a particular question that you might have on 74, 75, 76. And I'd be happy to help. So, anyway, I hope everything's going good and this wasn't too bad for you.